CP2 Exam Style Practice Paper 1, Question 6. This question involves complex numbers, as we can see from the very first part, where we've got a 12 plus 5i inside there, and polar curves. We've got r and theta appearing in the very first part of the question as well. In the second part, it talks about an Argand diagram, so we've got to be thinking in terms of loci. And finally, in the third part, it's asking us for the area of the locus described, which, depending on the question, will sometimes simply be a geometric scenario where you're having to use results about arcs and sectors and so on, or it might potentially even be, as it could be here, the area of a polar curve, and you have to use integration, polar integration. So we start with, as usual, our question plan. And I'm going to jot down the key results that I'm going to be making use of. In the first case, the fact that our most basic, if you like, the most fundamental locus definition will be z minus a in modulus is equal to r. In other words, the distance from z to the complex number a is always equal to some fixed value. And if that's the case, you're describing a circle centered at a with radius r. And I've made a note to myself here, write with a minus sign, because that's one of the most common mistakes people make. If we have z plus something, it's tempting to think that the center of the circle might be at somewhere like 12 plus 5i. But if you consciously rewrite it, as I've done down here, into z take away minus 12 minus 5i, then we can start to see more clearly that what we're looking at is the size of the gap between the point minus 12 minus 5i and the moving point z, which must always be a distance of 13 from that point. That's what gives it a locus of a circle. Now, if I can get that bit, which should be fairly quick, as long as I remember the minus sign, the next bit looks a little unfamiliar. It's not something that you'll have necessarily been expected to do up to this point. Instead of saying what's the equation of this in Cartesian form, it jumps straight to the polar equation. So it might be that you say, let's use the Cartesian equation in order to get a valid polar equation. You might do it that way. There are other ways through, and we'll look at both of those as we go along. The next bit talks about the argument as well. It's got minus pi less than or equal to arg z less than or equal to minus 3 pi by 4. So I'm using the fact here, I'm making a note to myself that because the argument is the anti-clockwise angle from the positive real axis, this describes all the arguments which are anywhere between southwest and due west. So anything from pointing directly to the left and then pointing diagonally down and to the left. That's the region I'm interested in there. You might do a rough sketch for yourself at this point so that you've got a rough idea of what you're expecting it to look like. And for the last bit, we're going to set up a polar integral for the correct region and maybe do a rough estimate to check that it's valid. We want to have some idea of whether the answers we end up with match what they should. And we'll be able to compare because we'll have a reasonably good diagram, hopefully. So let's jump in, see what it looks like. The first part, as we've said, we're comparing to the point minus 12 minus 5i. We need a distance of 13. And it might look like I've made a nice precise circle here with crossing points in nice places. You don't necessarily have to know for sure where it crosses, but hopefully in this case you would notice, especially if your diagram is done carefully enough, we've got 12 to the left of the origin and 5 down. So if the distance from the center to the edge is 13, that 5, 12, 13 triangle hopefully jumps out at you. They're not trying to give you a really obscure set of numbers here. They're giving you numbers that hopefully will mean something to you. You'll recognize the Pythagorean triple, and you'll know, therefore, that the origin forms part of this circle. That is fairly important. That it goes through minus 24, or that it goes through minus 10i is not quite so crucial. But the fact that it goes through the origin turns out to be quite a useful thing to have noticed. Other points that you might focus on when you're sketching your circle are the extremes, the top, the bottom, the left and the right. When someone makes a mistake with a question like this, it's often a mistake they could quickly check and spot if they had looked at those extreme points. So if we do a verification here by moving up 13 or left 13 or down 13 or right 13 and seeing if the point we get to really does have the correct size, that can verify it for us and we know we're on the right lines. Or we spot our error, we can go back quickly and change it. So how do we describe the polar equation for this? The Cartesian equation should be easy enough. So maybe we use that as a halfway house. We say, I've got the center, I've got the radius, so the Cartesian equation jumps out at us. This is year 12 A-level maths. And therefore, the Cartesian form of the polar curve should match that. And we can get that as well. If we start from the polar curve we were given, this may feel a bit backwards, but in order to prove that it can be represented by this polar curve, it's perfectly valid to start from this polar curve and show that it represents the same Cartesian equation. So, as is often the case when you've got an r on one side and coses or sines on the other side, instead of squaring the left to get an r squared, I'm going to multiply it by r. That'll give me r cos theta and r sine theta, both of which are quite useful pieces to have because they correspond to x and y. So on the left we get r squared, which is x squared add y squared. On the right we'll get something involving x and y, and we can rearrange a little bit now, which ends up looking like this. Looks a lot more like a circle equation. With a little bit of completing the square and rearranging, we end up at the same circle. Here's the alternative, which looks a little stranger, but gets us more directly, I think, to the polar form. So you start with z plus 12 plus 5i in modulus is equal to 13. But we notice that z can be written in polar form directly. We've got a polar form for complex numbers, so why not use it? Z is equal to r times cos theta plus I sine theta. And if that's the case, separate out the real components, the r cos theta plus 12, and the imaginary part, which is r sine theta plus 5. And if we want the size of this complex number, we square the real bit, we square the imaginary bit, we add them together, and that will give us the square of the distance. Now, if we expand all that out, it's a little bit messy looking, but there'll be some cos squared bits and sine squared bits that actually match up nicely. R squared times cos squared theta and r squared times sine squared theta is just r squared times 1. Then we have 24r cos theta, 10r sine theta, and a bunch of numbers that should go together and sort themselves out quite nicely. And once we get to this stage, we can rearrange, we can divide through by r, and hey presto, there's our polar curve. Now the second part of the question involves this locus here. So I've already drawn it on. We're expecting a 45-degree angle here because we're somewhere between minus pi and minus 3 pi by 4. Notice here where we said it's important to spot that your curve goes through the origin or through the point 0 plus 0i. And once we've got this, you might be thinking, okay, well, I want the area. This is a circle with a couple of segments taken out. So let's just work out the area of the segments. And you can do it like that. And I gave it a bit of a try and got bored and went back to the polar form because I think in this case, the polar form is the better form. There's often a reason why they set up a question the way they do. It starts out by describing a locus on an Argand diagram. It gets you to spend a few minutes turning that into a polar equation. And then it says, work out the area of this particular section of that polar curve. It sounds a lot like they're guiding you towards a polar integral. Not necessarily because they just need to test you on polar integrals, but because it's probably the most efficient way to solve this particular problem. So although you could be a bit contrary about it and find a different way through, it would probably take you longer and be harder to do. So let's see what it looks like when we use the more sensible approach, the polar integral, and then we'll briefly look at what the geometric approach might involve. The first thing to remember is that when you perform a polar integral, you are finding the sum of a whole bunch of tiny sectors. So think of it as half r squared theta, just like when you learned radians in the very first time you came across them, half r squared theta. And that means we're going to be adding up a bunch of half r squared d thetas. So it's the integral of half r squared d theta. Don't do what I did, which is a pi r squared, getting it mixed up with the volumes of revolution. You want to use half r squared theta, which becomes half r squared d theta. If you get the wrong numbers, pi is sufficiently bigger than a half that you should notice, and you'll go back like I have now and corrected it. So what you're seeing now is the perfected version. Remember to square r. Don't just integrate r itself, square it because you're working out the area of all of the tiny sectors. Now this is a little complicated because you've got sines and coses and you will need to expand out your bracket. when you've got sine squareds and cos squareds that don't have the same number in front, you can at least combine some of it. So some of those cos squareds, 25 of them, can go with the 25 sine squareds and give you just 25. But there's 119 cos squared thetas left over, and we've still got the 120 sine theta cos theta terms. Now those bits, hopefully you notice you've got double angles there, but also we have double angles here, just less obviously, perhaps. Cos squared theta is going to want to turn into something involving cos 2 theta, just so that we can integrate it. Once your integral looks like this, life gets a bit easier, because cos 2 theta and sine 2 theta are much easier to integrate than cos squared theta or sine squared theta, or indeed sine theta cos theta, which we would have had up here. So now we can perform the integral, we can sub the numbers in, and we can get an answer. And I would strongly recommend, because there are so many places where things can go wrong, that you check your integral with the calculator. It's quite a tricky one to do because you've got all this expanding out and simplifying, so there are many places where errors can creep in. So sub it into the calculator and see what number the calculator gives. And then you can also check by eye. I recommend you do both of these verification steps, because it's quite possible that you set up the integral wrong. That's what I did. My first mistake was setting up the integral wrong. I then subsequently made other mistakes with the integral itself. So in order to make sure you've got the correct integral in the first place, and then that you've evaluated it correctly, use the calculator, but also use some kind of rough approximation. We know the area of the circle is 169 pi. The area that we're looking at, according to our diagram, should be about half of that, maybe a little less. And so if we're getting 250 something, and the real area is 530, then that's a number we can be reasonably confident with. Now, just briefly, if you do decide to go down the geometric route, you can possibly get away with it in this case, because the question said, give your answer to 3 significant figures. So at the very end, we're not necessarily needing an exact value. Polar integration can give us nice exact values. It did here, for instance, but at the end, in order to get the final answer, we need to write 252 square units to 3 significant figures. That's something I didn't write in my plan, so it's something I potentially miss off at the end if I don't have it, if I can't tick it off at the end. If you don't go back and reread the question, you might well miss that. If we need exact values, this method on the right is going to be a bad choice, because, well, we can work out these angles easily enough, A and B, inverse tan of 5/12, and then pi by 4 minus that, but then you've got to do pi minus 2 lots at that angle to work out the bit inside, and then you're going to have to use that along with the area of a segment, which is the sector area minus the triangle area, so you end up with these nasty looking things. And of course most of this will be on a calculator, and you get approximate values all the way through. You'd have to save values and make sure they're accurate enough so that your answer is at least accurate to 3 significant figures. But notice that if you ever need an exact value, this method is going to be a problem for you.